In the late 1950s, the S-25 Berkut entered service around Moscow. The 75 product family followed, called the SA-2 family in the west, and was deployed around the strategic cities of the Soviet Union. It started with the SA-3 Neva, which was followed by the very short-lived S-75 Desna in 1959. From 1961 onward, the S-75V was deployed, then the M variant. These systems have been presented previously. The basics regarding missile guidance and any other related topic are not repeated in this video, therefore it is highly recommended that you watch them. The most relevant parts of the previous videos are linked down below in the video description with a timecode. Let's start then. All the listed air defense systems in the Foreword were designed against medium and high altitude and possibly high speed targets. What happens if the opponent realizes the insufficient low-level capability of these SAMs and tries to deal with this air defense by flying low? The low-level engagement capability of the S-25, the Dvina and the Volkhov were extended only in the late 60s. Upgrading them in this era is strongly limited by the design of their fire control radar. The bottom of the scan zone could reach the ground when low-flying targets were tracked. Electromagnetic waves reflected from the ground or even from the water caused interference signals. This could obscure the target regardless of filtering. The reason for developing the S-125 Neva system was that the low-level capabilities of previous SAM systems were insufficient. Initially, they had a 3 km minimum engagement altitude, which were incrementally changed to 300 then 100 meters. When the development of the new SAM began in 1957, not even the S-25 Desna was deployed. Regardless, many features of the 125 Neva resembled those of the S-25V Volkhov. The Neva was developed by the Kibay-1 Bureau as well as the rest of the 75 product family. The similarities between them are not coincidence. Before our detailed presentation of the Neva, it is worth considering the factors which determine the engagement zone when low-flying targets are considered. The detection range of any radar is restricted by the radar horizon because of the curvature of the Earth. Using an ideally set flat terrain with 10 meters of radar antenna height, we get the following detection ranges: 35 km at 30 meters of altitude, 45 km at 60 meters of altitude, 55 km at 100 meters of altitude. Therefore, the expected first detection range is between 35 and 45 km against targets which are flying lower than the minimum engagement altitude of the upgraded Volkhov. The reaction time of a SAM missile battery at full alert was roughly 30 seconds in the late 50s. This covers the time between the initial detection and missile launch, assuming that missile preparation had been done previously. Then it takes time for the missile to reach the target, which is determined by the speed of the missile and the velocity of the target. Let's check the speed of the potential targets flying at 100 meters or even lower altitude. Targets above Mach 1.3 did not exist in the late 50s and not even today if we are speaking about manned planes. The maximum speed is restricted by the effect of the dense atmosphere, not only because of drag but even the heat load because of friction. But even this speed is theoretical because almost every manned plane would consume all of its internal fuel within 6-8 minutes. Such speed is achievable only with full afterburner and without external stores, or at least with empty pylons. So even just using the afterburner at low level for 3-4 minutes, it would reduce the range of almost any plane to an unusable level. We can state that the realistic top speed of any manned plane is close to Mach 1. However, subsonic speed region is more realistic at low altitude. Even the AGM-28 Hound Dog missile, which flew at Mach 2 at 17 km altitude, using its low-level attack profile, had only a Mach 0.83 top speed with a strongly reduced range. Therefore, the maximum engagement speed of the new SAM would be lower. It was more than enough to be effective at targets up to Mach 2. This still made it possible to destroy many types of higher flying targets if the system had to deal with them. Now let's calculate the edge of the engagement zone considering all the listed factors. Let's consider 35 km first detection range, 300 meters per second target speed, about 10 km flyby distance, and 30 seconds between detection and missile launch. Following initial detection, at the moment of the launch, the distance is about 26 km. If we assume 600 meters per second for the missile's mean speed, the intercept point would be about 17 km from the same site. Therefore, designing a missile with longer kinematic range is unnecessary because it simply can be utilized because of the capabilities of the electronics and automatization of the era. Many manual activities and human decision needed before the launch. In fact, this model neglects the time between first detection and passing the data to the fire control cabin, so we can consider this model optimistic. Let's keep in mind this consideration because it will be important later to understand the design basis of other SAM systems. Because of the limitation of the fire control radar and the radio command guidance at the time, the missile has to stay low during its entire interception trajectory if the target flew low. But this also means that a missile designed against low-level targets up to about 20 km distance could reach a very high altitude. As the altitude increases, the density of the atmosphere decreases. Regardless the missile has to deal with gravity, thanks to the much reduced drag, the burnout speed of the missile is higher even if the missile performs a steep climb. We could see previously that the S-125 Volkov had a longer engagement range against high-flying targets. Even so, the S-125 Neva was designed specifically against very low flying targets, yet it could engage targets at high altitude. The Neva was similar in basic unit composition and cabin interior appearance to the Volkov, but it can be considered a simplified and rebalanced version of the latter with different main equipment. The missile battery, as usual, had a target acquisition radar, but the range of it was smaller even compared to the P-12 of the Dvina. Because of the smaller engagement zone of the missile, a shorter range radar does the job well. Instead the P-12 or P-18, the Neva initially got the P-15 and later the upgraded P-19 radars for searching. The point of these different radars was to provide low-level search capability. Both the P-15 and P-19 had 300 kW peak impulse power, which was higher than the 260 kW of the P-18. The reason for the higher power was the SDC mode. The ground clutter filtering of the radar demanded high output transmit power. Because of this, targets outside the ground clutter could be detected from a relatively long range. The point of the design of the P-15 was its low-level search capability, but this design goal limited the maximum target altitude. The design of the antenna had a strong impact on the lobe forming. The era of the universal radars had not yet come. Both the P-15 and P-19 had about a 140 km maximum detection range against the MiG-21 size fighter in the medium altitude zone. But the detection range decreased as the altitude decreased. At 3000 meters it was 120 km, at 1000 meters 80 km, at 500 meters 70 km, at 300 meters 50 km, and finally at 100 meters it was only 30 km. Above 6000 meters altitude, small fighter-sized targets could not be detected at all with the P-15 or P-19. But compared to the P-12, which had a 1000 meters minimum altitude as 30 km distance, the P-15 achieved 100 meters lower limit. The deeper explanation of this topic and several others are in the extra content for the Patreon supporters. During its service, the P-15 was further developed, which resulted eventually the P-19 radar. This is basically a more advanced form of the P-15MN variant with better low-level and ground clutter search capability, otherwise their capabilities were almost the same. Not every operator acquired the P-19, however some operators allocated the P-18 to their missile batteries. The Neva was able to handle two target acquisition radars, so the P-18 was responsible for medium high altitude search and the P-15 or the P-19 for the low level. The basic working setup of the SNR-125 fire control radar was inherited from the Volkov. Compared to the SNR-75, the receiver antennas tilted 45 degrees compared to the exactly horizontal vertical scan directions. This antenna setup could reduce the reflection from the ground when a low-flying target was tracked. For the Dvina and the Volkhov, the left-right scanning antenna received lots of ground reflections. Thanks to the tilted antennas of the new fire control radar, only a very small area of the joint scan zone reached the ground. The fire control radar is similar to the Volkhov, even it does not appear to be. However, it is simpler, smaller, lighter and has fewer antennas. Moreover, there is not a cabin with a crew directly below the antenna. The main components of the fire control radar are the following: UV10 3 cm wavelength narrow beam transmitter receiver antenna, UV11 3 cm wavelength wide beam receiver antenna Phi1 angle, UV11 3 cm wavelength wide beam receiver antenna Phi2 angle, UV12 decimeter wavelength missile commanded transmitter antenna. The Neva could perform only a narrow beam search and the LORO missile guidance, which was very similar to the LORO mode of the Volkhov. Let's start with the narrow beam search. In the case of the Volkhov, the elliptical narrow beam search covered a roughly 5 by 5 degree area and a little more outside using two parabolic antennas. While the SNR-125 with the UV10 antenna using a 1.5 degree wide pencil beam scanned 10 degrees in elevation. Therefore, the fire control radar scanned only a 1.5 by 10 degree zone. Of course, the center line of the scan zone in azimuth could be set to any direction by rotating the antenna structure. Considering this very narrow scan zone, it is understandable how limited the self-search capability of the fire control radar was without the P15 or data link to a higher level command post. A target acquisition radar is essential if intercepting medium altitude targets was also a priority. Even if the system found the target by self-target search, it had essentially no situational awareness without a target acquisition radar. Because the system was designed against low-altitude targets, its ability to search for targets was optimized accordingly. Some Western sources claim the PRV-10 or PRV-11 High-Finder radar was part of the missile battery, but that is not true. They are simply not needed. Considering the target parameters, the engagement zone and the target lock process, which was described for the S-125, was not necessary to accurately measure the flight altitude of the targets. Because the Neva basically was designed against low-level targets, the azimuth data was provided by the P15 radar. Based on the data of the target acquisition radar, the SNR-125 was rotated to the direction of the selected target. The bottom of the scan zone was just set above the ground level. Then, the selected target was found with some degree of left-right manual rotation of the antenna structure. For whatever reason, if the fire control radar had to be used for target acquisition, it was possible to perform a sector search or even a 360-degree search. In these cases, the antenna structure was rotated left-right in the defined zone on 360 degrees. This could be done manually or automatically. The sector search had sense if at least the main direction of the incoming threats were known. In such cases, for example, the antenna performed a left-right plus-minus 20 degree scan with a defined center. Assuming a perfect westward main threat direction, this could for example be scanning between 250 and 290 degrees direction. In such instances, the only reasonable goal was to detect targets appearing behind the closest obstacle or finding a target which just appeared above the radar horizon. But this kind of long scanning is suicidal when the opponent employs anti-radiation missiles. Because of these factors, the self-search capability of the Neva was inferior compared to the narrow beam search of the Volkhov and far inferior compared to the wide beam search of the Dvina and the Volkhov. The latter had a 7 by 7 degree zone where both the azimuth and elevation of the target could be measured, while a target appeared on at least one of the screen if one of the lobes hit the target. Following that, a quick correction was possible in order to track in elevation and azimuth the target. For guiding a missile to a target, the LORO mode was required. The Neva did not have similar wide beam mode comparable to the SA-2 family. The UV11 antennas were only receivers, they received the reflections generated by the single UV10 transmitting antenna. The UV11 receiver antennas were necessary to track the missiles and the target. Both the UV-10 and UV-11 antennas measure the distance of the target. This makes the range gain pull-off type jamming harder. Because the missiles were not necessarily in the scan zone of the UV-10, the UV-11 antennas received the response from the radio beacons of the missiles. Consider this analogy: 3 men standing in a line next to each other. The middle man with a flashlight tracks a moving target. The other 2 people can see the light reflection from the target with their eyes and also can see other light sources. But how could the system scan in 2 directions with a single emitter? The 2 UV-11 antennas are scanning while following each other, first in the phi-1 direction, then in phi-2. Both scans need the UV-10 transmission, but the scan happens so rapidly that for the human eye the display on screens seems continuous. Because of the narrow beam and the LoRa mode, detecting an incoming anti-radiation missile was possible only when the already tracked plane launched it. Both the Dvina and the Volkhov could detect such a threat in a larger zone if they used wide-beam search. Even in the AGM-45 Shrike era, it was very uncertain if such a threat would be detected. Not to mention the AGM-88 Harm era from the mid-80s that totally changed the combat environment for the SAMs. Performing long target searches with the SNR-125 then guiding a launched missile became very dangerous when one could expect a new anti-radiation missile threat. The general appearance and look of the Neva was barely different from the S-125 Volkhov, even the fire management cabin was similar. The Neva in many ways was the simplified, more user-friendly and rebalanced brother of the Volkhov. It is a clear sign of this approach that the S-125 had only 2 missile channels compared to the 3 of the Volkhov. Of course, the Neva also had a single target channel. In short, the Neva could track and attack only a single target, guiding 2 missiles on it at the same time. The Neva used the same radio command guidance method used by all of the previously presented SAMs, the Berkut, the Dvina and the Volkhov. The missile could use the half-leading or the 3-point guidance methods depending on the need and type of the tracked target. Against very low targets, some special variants of the K method were used. These were selected automatically by the system, the crew got only feedback about them. Optical target tracking was performed with the same Karat TV camera that the Volkhov got later. The Karat was only available only for the S-125M and M1 variants. Because the Neva was designed against low and very low targets, it was essential to have the filtering ability in case the target was in ground clutter. Therefore, the Neva from the beginning had the SDC equipment. Of course, this feature was also true for the P-15 target acquisition radar. The GSN circuits against angular deception jamming were built into only the M1 variant, but later older versions got it as an upgrade during the regular overhauls. Instead of the 2 waveguide channels of the Dvina and the 4 of the Volkhov, the Neva had only 1. These were hermetic, angular, arm-sized stick channels. The mobility of the Neva increased thanks to this and other later presented features. The complex had an additional cabin and antenna for electronic identification friend-or-foe capability. The Neva did not have its own equipment for it, just as the Dvina and the Volkhov did not. The IFF issue was taken care by the target acquisition radar or by the higher level automated command post. The restrictions of the engagement zone because of the general technology level of the era and the radar horizon have been already mentioned. The missile simply did not have to fly as far as was demanded from the Volkhov. This resulted in a much smaller and lighter missile. The missile still had 2 stages, but the launch weight was significantly lighter. Compared to the roughly 2,400 kg missiles of the Volkhov, the Nevas were only 950 kg. The warhead also was lighter. The first major missile variant of the Neva, the V600P, had 52 kg warhead, which increased to 72 kg for the V601P missile family. Even the latter is far lighter than the 200 kg warhead of the Volkhov. The reason of this difference is explained with greater detail in the Patreon extra content along with more in-depth analysis of the other systems. The smaller kinematic range of the missile made further simplifications possible. Regardless, the specific impulse of the solid propellants at the time was much lower compared to the missiles developed 20-30 years later. It was already good enough. The propellant was nitrocellulose. This made the maintenance and operation with the missiles much easier. The missiles of the Berkut, Dvina and the Volkhov system used a very toxic, corrosive and volatile propellant, therefore the crew had to wear a fully enclosed chemical protection suit. This was not necessary for the Neva. The propellant always was in the missile, it never had to be removed. The missile battery did not need missile and oxidizer fuel transport vehicles. This difference not only made the service of the system easier, but also increased its mobility. Regardless of the decreased kinematic range of the missile, it still had two stages. Both stages used solid propellant. The thrust of the second stage could not be controlled as it was for the later missiles of the Volkhov, but the smaller engagement range simply didn't demand such a feature. The 225 kN thrust of the booster stage accelerated the missile to 600 m/s in under 3 seconds. The engine of the traveling stage had a 20 kN thrust, the burnout time was 19 seconds. Depending on the trajectory of the missiles, which means target altitude, the peak speed of the second stage was between 750 and 950 m/s. The quantity of missile launchers was reduced from 6 to 4 compared to the SA-2 family, but the number of missiles stored on them increased thanks to the smaller and lighter missiles. On each 5P-71 launcher, 2 missiles could be stored, while on the later developed 5P-73 model, 4 could be stored. So, in the beginning, the Neva had 8 missiles ready to launch, while later was increased to 16. The total missile inventory of a single battery increased from 24 to 48 with the 5P-73, but 60 missiles were at the tactical battery. Thanks to the experiences of proxy conflicts of the Cold War, it was learned that missile quantity was indeed a priority for later SAM systems. Nominally for the Dvina and Volkhov, the rules of engagement dictated a free missile salvo against maneuvering targets. Therefore, they could engage only twice, considering it had only 6 missiles before the system had to be reloaded. Compared to this, the early Neva had 8 missiles on launchers, so it could engage 4 times with 2 missile salvos. Following the introduction of the 5P-73 launchers, the number of engagements before reload increased to 8. The 5P-73 launchers were available only for the M and M1 Neva variants. Reloading of the launchers was possible from the PR-14AM TZM missile transporter and reloader vehicle, which was built on a ZIL-131 truck. A fortified missile battery had 2 fortified platoon entrenchments with 8 TZM vehicles carrying 2 missiles on each. For the S-125, basically 2 major missile variants were developed, but only the second one got any major additional upgrades. The early V600P 5V24 had only a 14 km maximum slant range, while the V601P 5V27 had a 25 km range, considering the passive trajectory phase of the missile. The minimum engagement range with the V600 was 6 km, which was reduced to 3.5 km for the V601 missile. The maximum target altitude with the V600P missile was 10 km, which increased to 18 km for the V601P. The minimum engagement altitude was initially 200 meters for the V601P. The 5V27 variant reduced that range to 50 meters and finally to 20 meters with the 5V27D missile variant. The maximum G load of the V600P missile was 8G, while the best missile variant at medium-low level was able to perform turns up to 18G. The latter value was far higher compared to the best missile variant of the Dvina and Volkhov, which peaked at 9G. Therefore, dodging the missile was a considerably harder task for any tactical plane within the active phase of the missile, as long as its engines still produced thrust. At the edge of the engagement zone, deceleration of the missile happens quickly, which strongly diminishes its turning capability. Even so, the engagement zone of any Neva variant was smaller than what the Dvina or Volkhov had. But within its zone, the Neva was more suitable against highly maneuverable targets like tactical fighters or strike planes. The better maneuverability of the missile was ensured by the placement of the canard control surfaces before the wings of the missile. The missile preparation time was initially 2 minutes, but like the Volkhov, it was reduced to 30 seconds for the 5V-27U missile variant. Like the Dvina and Volkhov systems, the Neva could launch and guide a missile against a land or ship target, although this is more of a theoretical capability in case of an emergency. Thanks to the later upgrades on the fire control radar and missiles, the maximum slant engagement range increased from 14 km to 25 km. But it has to be noted that above 17 km was the passive phase of the missile. At that range, it was only effective against subsonic targets due to the rapid deceleration of the missile. The initial maximum 560 m/s target speed increased to 700 m/s for the S-125 Neva variant thanks to the upgrades and the 5V-27 missile. The most advanced Neva variant, thanks to its 3.5 km minimal engagement range and 20 meters of minimum altitude, was effective against planes equipped with terrain-following radar flying at 60 meters of altitude. If the crew of the missile battery was highly trained, skilled, fast and a bit lucky. Such targets were the F-111 or the European Tornado fighter bombers. Here is the engagement zone of the S-125 M1 Neva. On the left side is the diagram with the engagement zone against targets under 300 m/s speed. On the right, between 300 and 700 m/s with 97% hit probability. Targets are considered non-maneuvering without applying any type of jamming. The meaning of the arrows on the diagram are the following. The pink arrow shows the edge of the engagement zone with a 10 km flyby distance. The end of the dashed pink arrow is at the same place as the solid arrow, but extending the direction, it is apparent that the target flies directly to the missile battery. So in reality, this case is the same as with the yellow arrow. Through these examples, it can be understood what is considered the flyby distance and how the diagram can be rotated to present possible engagement scenarios. The red arrows points to the line of the minimum engagement range. The black arrow points to the minimum engagement distance lines at 14, 16 and 18 km altitude. The 17° zone line limit can be seen as the side view of the engagement envelope. The green arrow points to the minimum engagement distances in case of different altitudes with the 3-point guidance (TT) and with half-leading (PS) method. The fire control radar can turn and track during the engagement when the target passes by the battery with a certain flyby distance. The Neva was able to guide missiles against receding targets, but its zone was more restricted compared to the Volkhov or Dvina. It was possible only against subsonic targets and the zone was not fully circular. On the above and bottom diagrams, the maximum and minimum engagement distances are pretty clear and simple. The continuous line shows the edge of the engagement zones. But against targets below 500 meters of altitude, the zone is significantly smaller, it ends at 11.5 kilometers. As long as the engine of the missile is in operation, the minimum target altitude is 20 meters. But in the passive phase of the trajectory, the minimum target altitude is 500 meters. The Neva had several special low-level guidance modes. These were automatically selected by the system. The operators had only feedback about them. These special guidance methods made very low-level engagement possible, where the Berkut and Volkhov system lacked that engagement capability. Of course, a Neva missile battery was more than just radars, missile launchers and missiles. In this chart, some of the main equipment is displayed. As the Dvina and the Volkhov, the Neva could be deployed to unprepared position as long as the conditions of the soil made that possible. In the Warsaw Pact, Neva missile batteries typically were deployed in fortified launch areas. The typical deployment layout made these sites easy to recognize. In many countries, Neva batteries formed a joint SAM barrier alongside Volkhov batteries, with the two complementing each other. Due to having fewer waveguide channels, the deployment and disassembly time of the missile battery was shorter compared to the Dvina and the Volkhov. The deployment time of the Volkhov was 2 hours and 30 minutes, the disassembly needed 1 hour and 45 minutes. These values were 2 hours and 2 minutes and 1 hour and 20 minutes for the Neva. Here is a picture about a Petra missile battery in the Middle East. The Petra was the export variant of the Neva to the third world countries. There are only 3 launchers with 4 missiles in the image. In the middle are the S-125 radar and the UNV and UNK cabins. The red arrows are pointing to them. The cabins and the launcher are protected by ramparts, as were other members of the SA-2 family. The main variants of the Neva were the followings. The S-125 Neva SA-3A with the V600P 5V24 missile entered service in 1961 in the Soviet Union. This variant had only the 5P71 2 missile capable launcher. The minimal engagement altitude was 300 meters. Small quantities were exported to Poland, Czechoslovakia, Egypt and Iraq starting in 1969. The S-125 Neva M SA-3B with the V601P 5V27U missile entered service in 1970. This variant got the quadruple launcher as well as the Karat TV system for optical tracking. The minimal engagement altitude improved to 50 meters. The Neva M was exported between 1973 and 1983. The S-125 M1A SA-3B with the V601PD 5V27D missile entered service in 1978. The minimum engagement distance was 3.5 km. The minimum engagement altitude was 20 meters. The anti-jamming GSM electronic package was applied to this version. The M0A variant was exported between 1983 and 1989. The variants exported outside the Warsaw Pact got the name Petra. The proxy wars of the Middle East had a very strong impact on the export of the Petra. Thanks to the big accumulation of the Six-Day War in 1967, the Soviet Union flooded Arab countries with the new SAM systems, beside many other weapons. In 1917 alone, 40 missile batteries were exported. Until the end of 1973, the year of the Yom Kippur War, another 45 batteries were exported. The Petra system was exported to Soviet-friendly countries of the Third World in far greater quantities than to the Warsaw Pact. Following the end of the Cold War, most of the operators retired the Neva within a decade, as they did to the Volkov or the Dvina. From the 70s on, the Petra participated in many proxy wars of the Cold War. It was extensively used in the Arab-Israeli conflicts. While the S-125 missed the Vietnam conflict because of the naval blockade by the US. The only way to transport the heavy equipment to North Vietnam was only railway through China. Soviet leadership did not want to risk its new and best SAM system falling in the hands of China by accident. Vietnamese crews got their training and passed their live fire exams in the Soviet Union, but batteries were not delivered to Vietnam. Iraq used it during its war with Iran and against coalition planes in 1991 during Operation Desert Storm. Libya also used Petras against the US during El Dorado Canyon operation in 1986. In 1999, Serbia used the Neva to gain its most famous trophy. An F-117 was downed by a Neva missile battery. This success led to many urban legends and myths about the incidents, as well as an overestimation of the capabilities of old SAM systems and underestimation of the steel technology. But these are topics for another time. If you like the video, share, subscribe, ring the bell and follow the channel. You can support the channel via Patreon for exchange early access videos, voting on planned topics, and extra content is accessible, as well as regular updates about the projects.